Now that we know how to solve both exponential equations and logarithmic equations, we are going to use that knowledge to help us to start to apply um, mathematics into everyday life. Now, not everyone's going to use these techniques in their chosen field, but those that do go into this field will need to know how to use logs and exponentials to solve for times, rates, and so on. So what we want to do here is we want to figure out how long will it take a piece of burned wood to decay to 16.2% of its original amount of carbon-14. This is how people carbon date things so that they know how old they are. And we can assume that the carbon-14 has a half-life of 5,730 years, which means after 5,730 years, it's going to have half the amount of carbon-14 that it did before that. And then after that long again, it'll have half as much again, and it will continue to decay. And then the second thing we want to be able to do is determine how much carbon-14 will be left after 2,000 years if we started with 10 grams of that carbon-14 when this piece of wood died and was burned. So if we're looking at part A here, part A wanted us to find an amount of time. But before we can find the amount of time, we need to know the rate of decay of the carbon-14 in this piece of wood. So we're going to use the exponential decay function, which is similar to our continuous interest formula. And it's going to be A is equal to PE to the RT. And the book tends to use different letters, but it's the exact same thing. We have a final amount, an initial amount, we have a rate, and we have a time. And whatever letters you want to use, it doesn't matter because they represent the exact same things. So I'm going to start out looking at the half-life of 5730 and use that to help us to find the rate. So we know that we're going to end up with half of what we started with. So I'm going to say half of 1 is, and then the e is part of the equation. Rate, we don't know what it is, but we do know that it takes 5,730 years to go from 1 of something to half of it. And if you wanted to start with 10 and go down to 5, or start with 100 and go down to 50, it doesn't really matter. As long as we have an initial value, and then we have half of that initial value for the final amount. Now, to continue solving this, I'm going to divide off the 1, which isn't going to change anything, and then take the natural log to get rid of the e. So the 1 doesn't do anything for us here, but then I'm going to take this e and bring it over to the opposite side as a natural log, which is a log with a base e of 1/2 equals the 5,730 times the rate. And then to finish solving for r, I'm going to divide off the 5,730 from both sides. Those are gone, and then my rate is going to equal this ugly looking fraction over here. And I'm going to leave it as that fraction for now so that we can be more accurate in our calculations later. So then the second part of that was we wanted to know how long is it going to take to get down to 16.2% of the original value. So 16.2% as a decimal, if I change that, would be 0.162. So I'm going to use that value as my final amount. So 0.162, the initial amount would be 100%, or just 1, e to the rate that we found, natural log of 1/2 divided by 5730 and multiplied by the time, because that's what we don't know. So then if I want to solve this, I'm going to solve it basically like we did the last one. We're just solving for time instead of rate. So the 1 doesn't do us any good because it's multiplying by e. It's just going to give us e. But then I need to take that e over again and change it into a log base e, or a natural log, of the 0.162 and then equals the natural log of 1/2 divided by 5,730 and multiplied by the time. So then to finish solving for t, I can multiply by 5,730, and to get rid of the natural log, I'm going to divide by the natural log of 1/2, and that's going to equal t. So then at this point, I want to type that into my calculator. So 5730 times the natural log of 0.162 divided by the natural log of 1/2 ends up giving me 15,046 years, or 46.6. So I could either say 46.6, or I could round that up to 47 years. At that point, 15,000 years, rounding up or rounding down isn't going to make a huge difference. So it's going to be that many years it will take to get down to 16% of the original. So two-step process there. We first found the rate, and then we found the amount of time that it would take to get to our desired percentage or desired amount of grams. So now I'm going to extend this and say part B, I'm going to come over here, and I want to be able to find the amount of carbon-14 that'll be left after 2,000 years if we started with 10 grams. So I'm going to use the same equation to help us out. This A equals PE to the RT. And within that equation now, we know the initial amount of grams is 10 grams. E is the same E that we've been using for the exponential. And I'm going to use the same rate that we did before because that's going to remain consistent for no matter how much time we're going. So natural log 1/2 over this 5730, and we wanted to know how much is left after 2,000 years. So now we know the time, so I can multiply the exponent by 2,000, and then set that equal to our final amount. So if I know my entire equation, we knew the initial value, we knew the rate, we knew the time, I can just plug all of those in and figure out what my final value is. So I take my 10, multiply it by E, put in my ugly looking rate of natural log 1/2 divided by 5730, and then multiply that exponent by 2,000, and I end up getting 7.851 grams left over after 2,000 years. So we've done a couple of things here. We started out by finding the rate, because that's the only thing we really could find in the very beginning. And we did that by plugging in the time for the half-life and recognizing that I'm going to end up with half of what we originally had. Once we had the rate, we used that to solve for the time. And then once I had the rate, I could also, for part B, solve for the number of grams that would be left over after a certain amount of time. So each of these, we want to be able to find the rate very first, because once we have that rate, we can do a lot of different things with these exponential functions. But until we have that rate, there's not a whole lot that we can do. So always break it up into two pieces. First, find the rate, and then second, solve for whatever else it's asking for in the problem.